Okay, guys. So today I want to talk about the geometry of cross products a little bit. What that means primarily is I'm going to tell you three things, and then I'm going to spend a minute and give you rough starts to proofs to two of them. We'll see how long my hand holds out writing on the tablet here. I might get to full proofs, I might not. The other one is actually kind of hard to define in a precise mathematical way, so I'm going to leave that one out. So the three things, right, are when we take a cross product of two vectors, there's going to be three properties that that's going to have. So the first property, is actually going to be that the resulting vector is perpendicular to the two vectors we put in. So that's going to be thing one. It's perpendicular to both starting vectors. So what that means is if I take a couple of vectors like this, the perpendicular vector is going to be kind of out through my head, right? So when I draw vectors on the page, there's always going to be a little bit of weirdness because I'm going to draw a couple vectors. I'm going to be like, okay, so here's a vector A, here's a vector B down here. Those two vectors are sitting on this page, right? And so the perpendicular to those is either straight out of the page or straight into the page, depending on which order I do them in. And that's one of the things that's worth noting here. Remember, the cross product's not commutative. So it's going to matter which order you apply it in. So if I do A cross B, I'm going to get a different result than if I do B cross A. It's not wildly different, but it is different. So first things first, I get a perpendicular to both starting vectors. Second thing second, this is going to be a size thing. So the magnitude is the area of the parallelogram formed by the two vectors. So what I mean by that is when I have two vectors A and B like this, there's kind of a parallelogram formed. So the vector that goes from the beginning over here to this kind of meeting point over here, that's the vector A plus B, right? So this is me laying the vector B tip to tail with A and me laying the vector A tip to tail with B. So I've got my two kind of translated sides here, right? I've got a parallelogram. The area of that parallelogram is the magnitude of the cross product. I've got a neat little tool that you can use to play with that. Where did it go? Okay, so here's a neat little tool that you can use. Here's my parallelogram. I've got my vector A and my vector B here. This is in Desmos, so you can drag these around. And you can see that I've got the magnitude of the cross product here. I've got how long is A, how long is B. So right now they're about 4 long. And you can see that if I collapse them, I get a number that's basically 0 out of that. And if I bring them out to something kind of close to perpendicular and make them both about 4 long, I get a number that's about 16 here. Play with this thing a little bit, see if you can develop some intuition for this. It's kind of a cool thing to do to know this little geometry, and I'm kind of proud of this tool. Go through here and see if you can figure out how in the hell I made this calculation, because this is actually pretty cool. If you understand this thing completely, you'll be a long ways towards getting problems in the book done. Oops, wrong one. Okay. So here I've got my my second thing down, right? That's the magnitude is the area of the parallelogram. Another way of writing that is to write the magnitude of A cross B is equal to the magnitude of A times the magnitude of B times the sine of the angle between them. I want you to take a second and see if you can take this picture apart a little bit, maybe like draw an altitude in here, put maybe an angle theta over in this corner. See if you can convince yourself that this is the formula. This is pretty cool. We're gonna actually get a chance to demonstrate this, or at least start thinking about demonstrating it. And then the third one, the one I'm not going to demonstrate today is, okay, if I've got two vectors, right? My two vectors on the page, right? A and B. I know how long the result is. So that means that it either has to be pointing straight out of the page and be that length, or has to be pointing straight into the page and be that length. Now, I'm not sure which one it is. And the way I tell is with this thing called the right-hand rule. So I'm going to look at my two vectors, right? So I've got A and B there. A is kind of on top. So I'm going to sweep my hand through A to B. I'm using my right hand here. And for me, what that means is that the vector A cross B is going to point into the page. So if I did B cross A, I would sweep my fingers the other way and my thumb would point in the opposite direction. So the right hand rule tells you which way the vector points. So those are my properties. The one that's actually hard to demonstrate is the right hand rule. To demonstrate my orthogonality, right? So let's spend a second with thing one, right? Just a slightly heavier marker. So for thing one, I need to take my cross product and dot it with A or dot it with B. If I can get 0 out of that, I'll know it's perpendicular. So I'm going to do it for A. So I'm going to take my vector here. Oops, come on. Okay, so all this ink is my vector A cross B, right? And I'm just going to drop a second copy of this down here for some reason. Don't worry about why. I'm going to dot this with A1, A2, and A3. Right, so this is going to be A crossed B dotted with A. Okay, so that's going to be equal to, I just want to rearrange the way this looks a little bit. Okay, so we're talking about thing one. I'm talking about A cross B dotted with A. So I wrote it out component-wise, right? And now I'm going to actually do this calculation. So I'm erasing commas and angles, and I'm going to take this first thing, I'm going to multiply it by A1, and I'm going to add. And I'm going to add this second component of my cross product multiplied by A2. And I'm going to add my third component here multiplied by A3. And now we're just going to do a little arithmetic. So I got A1, A2, B3 minus A1, A3, B2 plus A3, A2, B1 minus A1, A2, B3 plus A1, A3, B2 minus A2, A3, B1. And then we're going to go, okay, let's see. So I've got an A1, an A2, and a B3. Do I have another one of those kicking around someplace? A1, A2, B3. Oh, yeah, sure enough. There's one of those right here. So those cancel. And I'm like, okay, so what else have I got? I've got a A2, A3, B1. Oh, shit, I've got an opposite of that over there. And last thing last, yep, I've got a minus A1, A3, B2, and I've got a plus that same thing there. So, yep, everything canceled. I got that this is 0. And so ultimately what that means, right, from talking about the geometry of dot products earlier, I've got A cross B is perpendicular to the vector A. Okay, rad. Okay. So now I should need to do this with the vector B. I'll let you guys do that. It's not any different. Same thing. Okay, so for thing two is where this is all going to get away from us a little bit. Let's see, what do I have on the clipboard? Excellent. Okay, so thing two, I want to show the magnitude is the area of the parallelogram formed by the two vectors. Okay, so this is going to take a hot second. So first things first, I'm calculating the magnitude of A cross B. And word to the wise, it's always easier to work with magnitude squared if you can. So I'm going to start with that. So I'm going to start with the magnitude of A cross B squared. And that's going to be the magnitude of this vector squared. And that's going to be equal to, and here's why I'm happy to be doing this on OneNote and not on the whiteboard. So I just need to take all the components of this thing, square them, and add them together, right? Oops, that was a bit much. Okay, so just shuffling here a little bit. We just got to put each of these in some parentheses, square them. So we're going to take those and square it, add it to these squared, and add it to these squared. So that's just me applying the like distance formula in 3D, right? And now this is the part that sucks because we have to actually do this. So we get a A2 squared B3 squared. And then I get minus 2 A2 B3 A3 B2s. So that's just two of the cross terms, right? And then I get a plus A3 B2 squared. Guess I should write this guy that same way. Okay, so that's just the first term, right? And then I got a plus, and I got a A3 B1 squared minus 2 A3 B1 A1 B3 plus an A1 B3 squared plus an A1 B2 squared minus 2 A1 B2 A2 B1 plus an A2 B1 squared. Okay, so I got this whole mess. Now I'm like, whoa, what all is in this crap here? Okay, so let's see. This is where you got to put your little thinking cap on a tiny little bit. Okay, so let me see. Hang on, I got some. Pause this. Okay, so this is where it's going to get a little messy. So I'm going to start accounting for terms, and we'll see how this goes. I may leave you guys with an algebra exercise here. So I'm going to count for these two guys, and I'm going to add an extra thing. So I'm noticing I've got A1 squared in both of those guys, and I've got a B3 and a B2 also squared. So to me, that says I've got A1 squared times B2 plus B3 squared, or each squared. And I feel like that's getting kind of close to the magnitude of B here. So I have the sneaking suspicion that I ought to be adding B1 squared in here somehow. So we'll account for it later. Let's see. Then I noticed that I've also got a similar gadget going on for A2s. See those guys? Let me mark these. So that's the single underline term. Then for double underlines, I've got A2 squared times, and that's times B1 squared plus B3 squared. That kind of is similar, right? But it's also missing a thing. Okay. And then I've got A3 squared. Let's see. And these are going to be under squigglesies. and that one's got a b1 squared and a b2 squared. Okay, and then I've got all these guys. Let's see. So those are A2, B2, A3, and B3. Here we've got A1, B1, A3, and B3. So those are different, right? This one's 2s and 3s, and this one's 1s and 3s. That makes me think this other one's 1s and 2s, and indeed it is. Okay, so none of those guys are doing me any good right now. You guys see that? So I'm going to say, all right, let me just copy those guys down. So I've got a -2, right? And then that thing's all times, oh, what the heck? Let me write these out. They're kind of crappy, but I've got A2, A3, B2, B3 in the first one. Then in the second one, I've got A1, A1, A3, and B1, B3. And then in the third one, I've got A1 and A2 and B1 and B2. Okay, so I'm going to introduce some extra terms here to see if I can get something that I recognize. Because right here, I've got A1 squared, I've got A2 squared, I've got A3 squared. That's feeling like I've got a magnitude of A starting up, right? I just can't factor them out because these are all different. So to each of these, I'm going to go ahead and to this one, I'm going to add A1 squared times B1 squared. To this one, I'm going to add A2 squared times B2 squared. And to this one, I'm going to add A3 squared times B3 squared. Now the kick is I can't just rando add those things. I got to subtract them too. So I'm going to subtract A1 squared B1 squared. I'm going to subtract A2 squared B2 squared. And I'm going to subtract A3 squared B3 squared here. You guys all see that? Getting a little wild. But out of that, so these first two, when they combine, I get A1 squared times the magnitude of the vector B squared. Out of these guys, I get A2 squared times the magnitude of the vector B, also squared. And out of these three, I get A3 squared times the magnitude of the vector B squared. And then I still have all this crap. So, that stuff's really gross looking. You see that? It's like kind of actually horrible. Not really super psyched on it. But I see something really convenient right here. Let me maybe keep going. I'm gonna leave myself a nice big question mark here. It's really actually just this crap, right? All stuck together. But I know I need to fill that line in. I just kind of want to see if I'm getting somewhere. I think I probably am. Out of these, I could factor a magnitude of B squared. And then after I factor it out, I've got A1 squared plus A2 squared plus A3 squared. That's the magnitude of A squared. Okay, that feels really good. I'm gonna leave you guys a little project because I think it's probably not gonna do you a lot of good to see me do this. But I'm gonna give you a hint. So here's the hint. I want you to subtract here, and I think you should be able to demonstrate to me that this is going to be the magnitude of A squared times the magnitude of B squared times like the cosine of the angle between them squared. Like, where would I get something like that? I want you to have a look at this thing and see if you can convince yourself that that's like a dot product squared. Because once I'm here, I think you see that I could factor out a magnitude of a squared, a magnitude of b squared, and then be left with 1 minus cosine squared theta. Then we could use a trig identity to turn that into the magnitude of a squared times the magnitude of b squared times the sine of theta squared. So I'm gonna leave you guys this little arithmetic exercise. See if you can sort out what we need to kind of do to this thing to notice that it ought to be like the dot product squared. I don't think it's really very hard, but I'm just want you guys to play too. So see if you can figure that out. It's not too bad. The right hand rule thing's really, really hard actually. You kind of have to define what right hand rule means in a mathematically appropriate way, and that's really tough. So the thing I want you guys to take from this is that the geometry of the cross product is just three things. It's perpendicular to both the vectors it starts with. It's as long as the parallelogram formed by the two vectors is big, and it follows the right-hand rule. Should be noted that that means that if you do A cross B and B cross A, you get negative the other one. So if you do B cross A is negative A cross B, which is important to realize. It's not commutative, but it's not commutative in a really predictable way. So that's cross product geometry. This video is long enough. Thank you guys for watching.